Today's topic is continuing on the theme of testing, but it's with a particular extra take, and that has to do with testing of object-oriented systems. Many, although not all of you, are building your systems in languages that are object-oriented languages, whether it's C# or Objective-C. These are languages that are designed for supporting object-oriented development. And object-oriented languages are the dominant languages out there today, although they are increasingly being supplemented with support for other paradigms such as functional programming. Even languages like JavaScript, for example, are used in an object-oriented way in many cases. JavaScript is one of these languages that can be used in many different ways. You can use JavaScript in a functional way, use it in an object-oriented way, using it in a more procedural way. And so many of the principles here, although by no means all, will carry over for that context as well. So early on, object orientation in programming languages was first really introduced as an idea back in the 1970s, but it wasn't until the 1980s that there was a wave of practical support for a number of very practical object-oriented languages. And well before that point, Smalltalk was around, and Smalltalk has had a lot of pronounced practitioners, but it wasn't until the late 80s that, for example, you start to see C++ support. And I believe Objective-C came around a little bit later than that. And there's a proliferation of other object-oriented languages. And much of the motivation for these languages, by no means all, but much of it, there's an important thread of it that was focused on this idea of driving reuse and improving software quality. The idea was that object orientation, by allowing us to define these classes, would allow us to reuse software components. So we'll be able to reuse the same class in many different software projects, right? And we might or might not have access to the source code, but we could reuse that same object in lots of classes. And there was a thought that this would really reduce testing burden, improve quality and reduce testing, because we would test it once and then be able to reuse it in many places. And the thought was that might dramatically improve the quality of our software systems. And unfortunately, we didn't really see that for a number of reasons. There were benefits gained. After all, you don't spend your time debugging java.object, the sort of root object within Java. A lot of the Java library classes, you don't spend your time debugging. So, there's some advantages, but testing has remained as important, or even more so, partly because we're building larger and larger systems. But one thing that really has come to the fore since those early days, these sort of heady early predictions about how object orientation would radically change and improve quality within our systems, is people have recognized there are really distinctive risks associated with object orientation. That when you build an object-oriented system, when you build it with a language that's object-oriented, there's certain things you have to worry about that were quite different from what people had to worry about using previous approaches. And really this requires different testing regimes and so on. It's not so much that object-oriented languages are bad from the standpoint of testing, it's just you need to be conscious about certain additional things to test. And if you have a sense of where to look for the vulnerabilities, you can sometimes focus your testing effort in more fruitful ways. Now, there are a number of particular classic failure modes with object orientation. I'll list them up here, and then I'm going to go into some in greater detail. Okay. One of them one of the most common, and one that those in 470 are going to hear quite a bit more about in the next few weeks, is this one here. It's issues of behavioral subtyping. It's issues of, is a subtype behaviorally, so as a nominal subtype, a subtype that you declare as being a subclass of this or implements this other interface, is it really behaviorally qualified to be called that? Is it behaving in a way that's compatible with the expectations you would have from the supertype? Okay, and it turns out it's really, really easy in an object-oriented language to cause terrible and subtle bugs by violating this issue. And this has to do with what's called the Liskov substitution principle. And we'll be hitting that later in this lecture, and for those in 470, in a big way, we'll be hitting that over the next 2 weeks. So here, it's a failure of the programmer's reasoning and sometimes imagination and thinking, okay, I'm going to subclass this other class, but then that subclass, which can be passed around as if it's an instance of the superclass, behaves in ways totally unexpected given your understanding of the superclass. And it turns out that can cause huge bugs because people only know about the superclass, and suddenly there's this thing passing around that's masquerading like an instance of superclass, but it behaves very differently. It can cause big problems. A second issue is that there can be issues with the implementation. So the first one is about promises made by the subclass compared to promises made by the superclass or supertype. This next one down is failures of implementation. So it turns out it's really easy to build a subclass of another class that breaks the promises of the superclass. It breaks how the superclass works. Or the superclass evolves and it breaks the subclass. It's really simple to do. And it can cause, again, lots of problems. Turns out there's also difficulty often tracking down where problems are because code goes from the subclass to superclass and back again, etc., in ways that can be confusing. You can have things like something that's intended to be a singleton instantiated several times by accident. And in general, we have this phenomenon known as encapsulation in object-oriented programming. What is encapsulation? Can anyone say? What does it mean for us to have encapsulation for a given module of the code?
You hide details.
Yes. Good. You're hiding details. You're separating the interface from the implementation. The people who are using this module are not counting on all the details of the implementation, hence hiding details. What they're counting on is an interface, which is guaranteed, that only guarantees certain things. And that encapsulation is key for us to build scalable software systems. But the problem is that from the standpoint of testing, sometimes we can't look inside a given object because of this encapsulation. We don't have a way of looking inside it and saying, hey, what's the current state of that thing? And it makes testing more challenging because we don't know everything about the internal state. We can't test, oh, does it match this criteria or not? You know, is it problematic in this way or what have you? Instead, that code has to be inside the class, typically. And it turns out that for those in 470, this will be particularly fresh, but when you have generic types, when you have types that you have a type parameterized construct, like a type parameterized method or a type parameterized class, testing that is hard because it can be instantiated with all sorts of different types. And you can test it with a few types, but how do you know it works with a much broader set of types? How do you know it's going to work with any type people could instantiate it with? Not strictly an object-oriented issue, but it is an issue that comes up with a lot of object-oriented languages because of their support for templates or generics that they offer. Okay. And then there's an issue that I'm sure most of the people in this room have probably dealt with at one point, where you have a subclass constructor that doesn't properly initialize the superclass. So you have a constructor for your subclass. Maybe it's in C++, or maybe it's in Java, and it never properly calls the constructor for the superclass. And so the superclass data structures are they're not initialized properly. Has anyone been in that problem before? Had that problem before? Yeah? You didn't call off to the constructor, so the superclass is sitting there not being fully set up because you forgot to call its constructor. Okay, now these lead to a bunch of challenges, these failure modes, these classic sort of difficulties here. These lead to a set of challenges. How are you going to do unit testing if you can't look inside these objects directly? If code is sort of spread between multiple components that have to work together, A depends on B, C, and D to do its work. How are you going to test A when you don't have B, C, and D? Well, one of the answers to this is what? What do you do? Who are you going to call? Good call. I'll accept that for an answer. What I had in mind, though, is actually mocking. You use mocking, okay? And unfortunately, there's not a catchy song about that. But ladies and gentlemen, we mock, okay? If A depends on B, C, and D, instead of just having A always tested with B, C, and D, which is a problem if they haven't been written yet, right? And it adds to complexity of tests and debugging them if they have. What instead we do is we mock. So we mock out this, we mock out that, we mock out that. That's actually something that benefits from object orientation because A is maybe dealing with C through an interface, and we just have a mock of it, match that same interface, implement that same interface. And then A can deal with this mock of C as if it's the real thing, but it's just because it's going through an interface, it doesn't realize this is a mock. Mm-hmm. But it is something you have to consider, that in object-oriented code you have these needs. An important limit to mocking is, I don't know if you've ever thought about it, sometimes they have the impression that students may not be horribly troubled by it, but you can't mock a superclass. So if you're building a class, it's a subclass of another, and you want to test your class in isolation even from the superclass, that's real hard to do. Because it's a subclass of the superclass. How are you going to mock out the superclass and see if your class's code can work by itself? You can't really do that, right? It's intertwined with the superclass, right? You really need to test operations. If you define a subclass of a superclass, you really want to test the operations of the superclass in many cases to see if the subclass is operating properly. Why is that? Tell me why. Speak as in one voice. Okay, at least speak in many voices. Ghostbusters. Ladies and gentlemen, so why is it that you need to worry about operations in superclasses? All you've defined is foo, bar, and baz. Why do you have to worry about all these operations defined in your superclass, in the superclass?
Because your subclass might disrupt them.
Yeah, how might it disrupt them?
It might change, say, properties or attributes of an instance of the class that cause those operations to not perform.
Yeah, that's right. And in concrete terms, for example, you might override foo. Foo is defined in the superclass. You override it, and now somewhere up in the superclass, Zap calls foo, and you know, when that Zap was calling foo, when it was designed, all they knew about is the foo and the superclass. And now you've overridden foo. And Zap in the superclass is calling what it thinks is foo in the superclass. It's actually calling your foo. Think about that. And when it calls your foo, maybe your foo breaks it. It breaks Zap. Can you believe that? Yeah. And in order to find that mistake, that you might break aspects of the superclass, you need to test operations in the superclass. You didn't write the code in the superclass, but you may break the code in the superclass. You have to deal with the fact that you can't just get anything within an instance of a class. You can't look inside to see what its state is, so that may require setting up a testing interface for a class that's separate from the main interface. It's used for testing that class. And you know, in some cases it ripples through to, there's some other things, but I need to move on here because we have a fair bit of material to cover on this. But code reviews may require broader support, because now if you're reviewing A, you need to know something about how it depends on B, C, and D, and is it depending on them in a reasonable way. Okay, so we talked about encapsulation. Encapsulation gives us lots of good things. Modularity, separation of concerns, greater clarity, what's promised, flexibility in terms of evolving it. But it does mean, on the positive side, we can break up a system into pieces to facilitate testing. Each modular piece can be tested separately. And we should have a clear contract associated with which these pieces may be classes that are preconditions, postconditions, have invariance and history properties. And we can have nicely defined. On the other hand, it does mean that we need test hooks. We need often a class to be tested. Because outsiders can't look inside of it, we need methods in that class that sort of test, are things okay? Are its invariants maintained? Are things sane inside that class? Because we can't peer into all aspects of it. We need it to do some checking. So you may have a separate test interface that you have the main interface that's provided, and then a separate interface designed for testing that's used. And you want a clear statement of kind of this contract that's provided by a method or a class, okay? Like you're providing as part of your code bases. Okay, now I'd like to talk about this issue of that encapsulation can require consideration and testing. I want to specifically talk about type hierarchies and polymorphism. This should be familiar stuff. And for those in 470, again, this will be just dipping our toe into things you're going to be going into more detail here. Within Java, within Objective-C, other languages, within C#, we'll have hierarchies of types. And one of the big hierarchies that we have in Java, C# and others is we have these things called interfaces, right? What's an interface? Anyone tell me? How is an interface different from a class?
Defines a set of operations, but not their implementation.
Good, not their implementation, yeah.
It's like a contract that promises you that you're going to get something done given an input.
Yes, that's right. So it's associated with a certain contract typically. It provides operations and hopefully gives an understanding of what those operations do, what's guaranteed for them, what they need to do their job, what they guarantee if that's given to them. But it doesn't include the implementation typically. So this is an example of a hierarchy of interfaces. And this is in the context of the java.util library, right? So we have iterables and all collections, as an iterable, and a set can serve as a collection, which itself can serve as an iterable, and a sorted set is a type of set. It can serve as a set. We can pass it around as if it's a set, or we can pass it around as if it's a collection, right? Right? So if you have a reference to a collection, you take that in as a parameter collection for your function, for your method. Could you pass in a sorted set? And something that matches a sorted set. Could you pass in a tree set which implements sorted set as if it's a collection? Yeah, you could. Absolutely, you could. So anything below that in the hierarchy can be passed along as if it's one of these, right? So we say that there's a separation of a parent type. We pass it in as if it's a collection. You know, treat it as a collection. That's the, if this method and it accepts a, you know, this function foo accepts a collection of, you know, of person, right? As an argument, and we'll call it C, right? Here's foo. Here's foo. And we could pass into foo then an instance of a tree set, right? For that matter, an enum set or a hash set or a linked hash set, we could pass in as if they're a collection. Could we not? So we say inside of foo, all it knows is that it's a collection. It doesn't really care that much whether it's a tree set, a linked hash set, and a num set, right? These are all things that implement that collection interface directly or indirectly, right? True or not? In fact, we could pass in an array list, right? A linked list, a priority queue. All of these are collections, right? Now, that has real advantages. What advantage really sticks out in terms of that?
You don't need to define multiple methods for
Yeah, we don't have to have defined foo for tree sets, foo for linked hash sets, foo for enum sets, foo for priority queues. We just have one foo. One foo, ladies and gentlemen. You heard it here first, to rule them all. So, ladies and gentlemen, these type hierarchies give us a lot of advantages. They separate this actual type and a parent type, right? We say we program. Foo is, when we write foo, we program against the apparent type. It's as if we have an instance of the apparent type, even though we actually secretly have an instance of the subtype, as if we secretly have one of these guys here, but we're writing foo as if it's manipulating a collection, right? Now, tell me, when we call on this C, when we call some method, c.size, whose method is actually called? Whose method is called?
The one on the actual type?
The actual type's method is called, right? So maybe it's a linked hash set. And if linked hash set itself defines size, whose size is going to be called? Who are you going to call? Linked hash set. Good. I know you had to resist it. So, ladies and gentlemen, you're calling it on the concrete type, right? You're calling it on the subtype if it's defined in that. Even though it may be declared first, you know, that all collections support size, it's only called on the subtype, right? So, unbeknownst to it, foo is actually maybe calling size and linked hash set. Or could you believe this? You folks could actually implement your own collection, right? You could define a class which implements a collection. You could define your own set of methods, including size, and you could pass it into foo, right? And now whose foo is it going to be calling? Who's it going to call? Your size, right? Right? If you override size, you define collection, you define something that implements collection, you define size, and you pass it into foo here, which accepts a collection, it's gonna call your size. True or not? True. Okay. Okay, so ladies and gentlemen, dispatching is against, what we say is dispatching is against the actual type. It occurs on whatever the sort of the true underlying type is, right? So these sorts of type hierarchies are great. We can understand it, we can reuse code. Foo doesn't have to be rewritten for every type of collection. It's extensible. We can define new subtypes, and ideally, the idea was with the open-close principle, we don't have to modify the code of the supertype every time we subclass it, right? Every time we subtype it. Now, the risk here is the primary risk, one of two really big risks, and this is probably of the two, the one that's most keen, is that we may have something masquerading as if it's a collection, but it's really not. It's not a behavioral subtype. It's not implementing the promises, the contract of that supertype. Maybe it provides the size, but no matter how many things we insert into this class, the size stays the same. You could say, well, it's implementing size, but it's not really the meaning of size. You know, when we call size, we expect it to be the number of elements inside of it, and here it's returning, maybe it returns a random number for size, or returns -1 every time, or whatever. You could say, well, it's not true to the spirit of the superclass. That's not how it's supposed to behave. If you go and you iterate through each element of it, you should go through a number that's equal to the size of the collection. But you can have this disconnect between how it's actually defined and what it's promising in the superclass. And these fraudulent subtypes are pretty common. They occur quite frequently. And you folks can easily run in your careers to situations where you define accidentally a fraudulent subtype and it breaks people's code. It will break, put it over here, it will break this code because the subtype is behaving in ways that seem impossible given the contract of the supertype. So here the subtype is going to fail to ensure the behavior of the supertype that's being relied upon. So maybe this foo up here on the board that takes a collection is counting on some behavior that, you know, if I have this class and it has a certain size and I add something into it, its size can never go down, right? Size will never go down unless I delete something in it. And suddenly its size is, you know, I keep on calling size and I get different numbers. I don't even modify it, I get different numbers. It's randomly generated numbers. That would not be consistent with the meaning of size as defined by a collection. So this was formalized. This notion was formalized. People started to realize, wait a minute, we're getting in trouble with object orientation. People are using subclassing in different ways for different purposes, for code reuse versus for polymorphism, and sometimes it breaks code really easily. And Barbara Liskov and her student Jeanette Wing defined what is called the Liskov substitution principle, and that was, I think, late 80s, early 90s. And it's basically a guide to when subtyping is legitimate. When is this legitimate? For one thing, to subtype another. And the basic principle here, as they formulate this, is suppose that you have an instance, suppose that all you know about in the world are collections. All you know about is what a collection promises. And you reason for its contract through what the implications of that are. What's possible with a collection, for example. And that's what you know about, and you're reasoning about it. Well, any subtype that you want to create that claims to be a collection, that can be passed around as a collection, passed around as if it's a collection, that needs to guarantee any property that's guaranteed by collection. So if you can, using the contract promised by collection, if you can come to some firm understanding that only this is possible, then any subtype that claims to be a collection needs to adhere to that same promise. So if using the collection, you have a clear understanding that size will never decline or will never change unless you insert or delete something in this object. It will never change. If that's something that seems very clear from the contract provided by that superclass, then any subtype of it, anything that you implement that claims to be a collection, in the sense it can be passed around as a collection, as any of these can, it needs to adhere to that same thing. You can't willy-nilly define size in a subtype to return random numbers. That's not consistent with, doesn't jive with, it doesn't accord with, it violates the promises that are made by a collection. Why is that important? So who cares? Suppose we say, who cares? Who cares if it violates what people are counting on for collection? Why would that be dangerous? Suppose I'm writing foo long before you write your subtype, and I'm writing it with respect to a collection. I write this code with respect to what I know about collections. How is it that if you define years later a subtype which returns random numbers for size without even changing, inserting and deleting things from the class, why could that break my foo?
It can be used as if it's a collection?
Yeah, I'm using, so you could pass in an instance of your subtype as if it's a collection. But when I wrote this code, what I was counting on was what? The contract of collection. I was counting on the fact that I don't need to keep on checking the size on a constant basis. That if I'm not inserting something into it, it's not going to be changing. So I don't need to keep on checking it. I may be counting on that in the code. In other words, when I write code against a supertype, I'm counting on the properties of that supertype as I know them. And just because later, years later perhaps, you go and you create a subtype of your own, and you define it in some whacked out way, that shouldn't break my code, which is operating on collections. Indeed, much of the whole motivation here is we should be able to reuse code written once against a collection, and we can reuse it for any subtype. And if these subtypes can willy-nilly define anything in the way that they happen to by whim, then it can break code that operates on collection. It can break my assumptions, because I'm counting on the contract of collection, because that's all I know about. But you're passing in something which doesn't adhere to that contract. Does that make sense? So the example I use in 470 is, look, if you go to the FedEx website, and if you may read, okay, what are the criteria? What are the terms of reference? What's the contract associated with shipping a package to, Vancouver, right? You know that you need to get a package. Someone has a flight tomorrow midnight from Vancouver, someplace elsewhere in the world, and they forgot their passport here. You need to send them their passport, okay? And so you go to the FedEx website and you read on there, if you deliver this by 5 p.m. to FedEx in Saskatoon, it will be delivered to Vancouver by 5 p.m. tomorrow. That's part of a contract, right? If you go to that FedEx franchise now, a particular franchise here in Saskatoon, which I think there are several, if you go there and you fill out all the paperwork and you ship it by 5 p.m., you expect it, as in terms of that contract, to be there by 5 p.m. tomorrow, because that's what you read on the FedEx website, right? You're counting on that contract of the super type, the sort of set of all FedExes. Now, if that FedEx in town, if they said, well, we're FedEx, but we do things our own way, you have to deliver it to us by noon, or we don't get it to Vancouver. And sorry, it didn't get delivered till 9 a.m. the next day after the flight left. And they said, well, that's just our rules. You'd say, well, you're not FedEx, you're a fraud, right? You're not living by the FedEx contracts. I went to the website. Just because you're FredX, not FedEx, you can't decide any old rule, right? You have to live by, if you're claiming to be FedEx, you have to live by the rule of a FedEx. I'm dealing with you as if you're FedEx. I don't care that you're FedEx. I don't care about all the details of what goes on in your back office and your particular things. I want you to live by the rules. Now, if they live within the rules, were even better. If they said, look, you could deliver it by midnight the previous day, and we'll still get it by 5 p.m. the next day. Would that be okay? Different rule, but would it be okay? Yeah, if they actually allow you more latitude in terms of the preconditions, you're okay with it. But if they start saying, we don't guarantee what is guaranteed in the case of the super type, the FedEx, then it's a problem. So ladies and gentlemen, here, the idea is that anything that you could come to rely on based on the superclass, based on FedEx, you should need to be true of a franchise of FedEx, of the subtype. Yeah. So in order to make sense of this, you need to have something about specifications. It turns out that we can only prove these things. We can only rely on these things if we have some contract in place. And the way in which we put these contracts in place is with what's called a specification. We specify what are our preconditions and what are our postconditions. What things do we rely on to be true? What things are we counting on? What things do we need to do the job? And what things are guaranteed to be true if those things are ensured? Okay? And it turns out if you define those things, then you can start to reason about, okay, are the specifications of these ones compatible with the specifications of that one? Okay? And you could ask, in fact, is the implementation guaranteed? Now, a lot of the goal here is basic. You perform assertions against the specifications for classes, right? But you also test subclasses against the specifications for the superclass to make sure that you aren't inadvertently creating FredX when you're supposed to be adhering to FedEx's rules. You want to test all these subtypes against the specification for collection. Because it promises things, and someone, like Fu over here on the board, may be counting on the specifications for collection. Right? For all it knows, it was defined, that Fu was defined operating on collections long before any of these subtypes were defined. Just because a new subtype is added, it shouldn't break Fu, which is operating on collection. It's counting on the features of collection, right? And we need to test, therefore, all of these new ones against the specifications for this one to make sure that they don't break it. And then, thirdly, perform heavy testing on code that uses polymorphism. Here, you're going to want to particularly test to make sure that when subtypes are passed to code that manipulates supertypes, that it works properly. It's not just operating on one collection type, but it's on any of your elements that support collection, that foo will work properly. Okay, so this is subtyping. And what this had to do with was the promises. The thing that shocked us about FredX was that they didn't adhere to the same promises. They said, well, that's FedEx, but here at FredX, we require you to have the package in by noon. That's the only condition where we guarantee to have it there by 5 p.m. tomorrow. We don't, if, they say we don't adhere to the general FedEx rule of delivering by 5 p.m., we'll get it to there by 5 p.m. tomorrow. So ladies and gentlemen, that was all about promises, what we just talked about. Are the promises made in these subtypes consistent with the promises of the supertypes? But there's another side to it, besides these promises, okay? Besides this issue of fraudulent subtypes. And that has to do with subclassing specifically. subtyping without subclassing. So, for example, Q is a subtype of collection. They don't have implementations, but they are a subtype of another. The thing we're going to be talking about now is all about implementation. It's implementation together with the promises. So let's consider A subtyping B. We have a subclass relationship, right? So in Java, we have lots of subclasses. Lots of subclasses. These are some subclasses. We have some these things in the ovals here. What are those? Interfaces, ladies and gentlemen, interfaces. But these things, like writer and char array writer, or pushback reader and filter reader and reader and object, what are those? Those are classes. And these ones further down, an arrow from that to its parent means it subclasses it, right? It subclasses it. So here, line number reader subclasses buffer reader. What do you get by subclassing that? So what are the implications? If line number reader subclasses buffered reader, what are the implications of that? What does that give you?
It means that it's buffered reader. It works the same as buffered reader and extra.
Okay, something like that, yeah. Let me ask, I'll try to tease it out into two pieces. So line number reader and buffered reader here. So line number reader subclasses, it extends, right? In Java we write extends, right? It extends buffered reader, right? Suppose it extends it. Can we pass a line number reader as if it's a buffer reader? Yeah, we can. It gives us subtyping. We can pass it around as if it's an instancer. So all those things I just said about FedEx and FredEx and subtypes needing to adhere to the promises of supertype, all that's true. The promises made by line number reader need to be consistent with those for buffer reader. But there's something more than that. What else does what do you get with subclassing that you don't get with implements, with subtyping? What do you get extra? You get a set of goodies. What are those goodies?
Superclass implementation.
Yes, you get the implementation. You reuse the implementation, ladies and gentlemen. You reuse the implementation of buffered reader. All the methods that you don't override, right? All the instance variables, the fields within it, you get. You get the implementation of that, eh? From the FredEx standpoint, FredEx and FedEx, it's a little bit as if, I mean, it's one thing to FredEx to say, okay, we implement the FedEx rules. That's a subtyping relationship. It's another thing for it to say, we use all the FedEx IT system and network of couriers and planes and all that sort of stuff. That's a deeper sort of relationship. It reuses the implementation. And this is going to have huge consequences. Huge consequences in terms of coupling the two classes. Okay, so there's some real challenges here having to do with fragility, a situation where the evolution of or definition of one of those might break the other. So one possibility is that line number reader may break buffered reader's mechanisms. Because buffered reader calls off to a method which is overridden by line number reader. And that overridden method breaks how buffer reader was operating. That's one possibility. Another is buffer reader could evolve and line number reader still using its code, and now suddenly its extensions to that code break. The two are coupled together. They're tangled together in a thoroughgoing way. So the issue here is, and again, we're going to go into this much more in 470. The issue here is not only does that subtype, here, subclass, line number reader, have to be a valid subtype of buffered reader, not only does it have to make promises that are consistent, but it needs to be consistent with the implementation of that superclass, with the implementation. And it's tricky. That requires more information. I'd like to show you 2 examples of this, because this is sounding airy-fairy and sort of, you know, highfalutin. Let's go down to some very concrete things. Okay, so here's our superclass, and there's our subclass. Okay, so we have a superclass and to the left, and we have our subclass to the right. The subclass extends, in other words, is a subclass of the superclass. You see that? Right? Extends. Huh? Okay. Here's the superclass. What we know about the superclass, maybe we don't have full access to the code. Maybe all we have is this contract. It defines get value, set value, getters and setters, right? And something that asks, is it prime? Sorry, these things have to be 2 examples so I can fit them into a slide, right? Is it prime? Okay? Here's a subclass. This subclass overrides set value here, and it overrides get value, and it puts in place a new instance field that's actually the one, when we do set value, we write to that instance field. See that? When we do a set value here, we're defining this code. Maybe this code to the left was code we don't have access to, which is given, you know, it's something like java.object. We can't see its code directly. But this thing to the right, we write the code. And when we write set value, we assign to this new field, value current, right? This field we define. And when we do get value, we return the value of value current, right? Is this code going to work? Give me a reason to think the code might work, that could well work. Give me a reason to think it might break.
The getters and setters will work, but is prime could possibly be broken.
Okay, so why could is prime work? Give me a scenario where is prime would work. If it does what, it will still work.
If it uses the getter?
Yeah, if it calls internally inside is prime, if it calls get value, then it will is prime. Even though we haven't overridden it, it will call our get value, right? It's going to call. Remember, it's going to call the definition in the concrete actual class. It's going to call our get value. If anyone is uncertain about that, in object-oriented programming, if is prime calls get value, that calling is prime on this class to the right, that it calls get value, come speak with me. Because it's a very important point. Before graduation, you need to be rock solid about that. But if you have an instance of my super subclass 2, and you call get prime in it, it's going to, if it calls get value, it's going to call our get value, because we've overridden it, right? In that case, it could still work, right? Because this returns an int, this should be it, should say int there. It should return an int, and we're all good, right? So if it calls get value, so we need here an int, right? I don't know how that got left out. There we are, int. Okay, give me a condition where is prime would not work.
If it didn't use the getter?
Yeah, if it didn't use the getter, if whatever get here depends on is prime used directly, then when we call is prime for my simple subclass 2, an instance of that, it'll still be using whatever whatever field is up here, it won't be using our field, and therefore it'll be asking is prime about who knows what number, not the number we've set, right? So this might work, it might not work, and that's the whole point. We just through these standard specifications of preconditions, postconditions, we can't tell if this is going to work. We need to know at the least what is prime call, right? Does it call get value or does it not? We need to know that. But ladies and gentlemen, it's more than that. Let's suppose that through decompiling the code for my simple subclass, we could tell is prime calls get value. Why is that not enough? Give you a hint. That's the situation today. We're decompiling this, we see is prime calls get value. Why is that not enough? Just to know that right now it does that. It might evolve. If we don't have control over my simple superclass, if that's under someone else's control, who knows how that might evolve? Maybe today it calls get value. Maybe in the future some sort of optimization it doesn't, and it's going to break our code. Could you see why that would break your code? If this originally called get value, and then later they say, oh, we can make it tighter code by having it just depend directly on the underlying representation, then it breaks our code. Because now our class, where is prime used to work, it no longer works, eh? So there's an issue there. Okay, how about this one? How about this one? So here we have a hash set on the left-hand side, and then we have, this was adapted from an example in this great book, Effective Java by Block, which I strongly recommend. So we have a hash set on the left side that supports add all, and get count. Okay? And basically, you can add objects into this, or if you have a whole collection of existing objects, you can call add all. It will add all of them at once from the collection. And you can call get count to get the size. Gets the size fit. Okay? Great. Now, suppose we want to create an instrumented version of this. It's still the same basic thing, but we want to keep track of how many times we've added things into this. How many items have we added in? Whether through add or add all, we want to keep track of how many items have we added in. So we have an instrumented hash set. It extends, that is its subclass's hash set. And then we have an extra variable, which we maintain, add count, that we basically increment to sort of keep track of how many things we've added. Okay? So give me a reason that this code might work and might not work. Side note, add here, it simply adds 1 to add count, and then it calls add in the superclass. Just got the add over here. Add all here, it adds to the add count the count of elements in the collection we're adding. So we know we're adding all of those. And then it calls add all on the superclass. Why might this work? Why might it not work? Let me put it another way. What's a condition under which it would not work?
Add all calls add.
If add all calls add, whose add is it going to call?
Yours.
It's going to call our add, because this is overriding. I actually don't have an explicit overrides keyword here, but Java doesn't require one. It overrides the add up here. So calling add all on the superclass explicitly, super.addAll, will call add all, and if it calls add internally, it will call this add. And it's going to double count the things being added in, because we're going to count them once and add all itself. Then we're going to call them again for each of the adds being called. We're going to total up twice, right? Now, is it possible this would work? Under what conditions would this work? Or give me a condition under which it would work.
Add all doesn't call add?
Yeah, if add all doesn't call add, if it just loops through the collection and puts them into the internal set representation. It never calls add, then this will work just fine. And that's exactly the point, ladies and gentlemen. Whether this works or not is not clear from this specification. This specification and the one on the previous page might be perfectly adequate. Mark my words. It might be perfectly adequate for using instances of these things. So if we're just using them. But if we're trying to subclass these classes, the class here on the left, or the class here on the left, we need more information. We need to know who calls what. Which of these things? We need to know something about, ladies and gentlemen, dare I say it, the implementation. To subclass this safely, we don't need to know all details about the implementation, but at least we need to know what calls what, because in the subclass, by overriding methods, we could change aspects of the implementation, like which particular thing is being called by the superclass. Do you get that point? By creating a subclass, we are actually changing the behavior of the superclass. Now the superclass is calling different methods. If add all calls add, it's calling our add, not its add. So we could break assumptions in the superclass, or at least we need to know about the assumptions here, and the superclass could evolve. Maybe add all right now does call add, and later it doesn't, and it breaks our code, the correctness of this code. Do you appreciate that issue? Okay. Okay, so when we have subclassing, we're in a bit more of a pickle than just with subtyping. Yes, we have to make promises in the subtypes, adhere to promises in the subtypes consistent with the supertypes. Yes, if we're red X, we don't have the latitude of saying you have to deliver your package by noon to get it there by 5 p.m. if red X allows you to deliver by 5 p.m. to get it there by 5 p.m. the next day. That's an issue of promises. And certainly we have to adhere to that as a subclass. But we also need to know more about the superclass implementation. We need to know about something about how it's implemented in terms of what calls what. Eh? Now, I noted, why not depend on the superclass code? Just say, well, I have access to the code. There's an open source system. I could decompiling it. It doesn't help. That just tells you what the current implementation is, and it doesn't tell you how it evolved. We need ladies and gentlemen, what do we need from the superclass? We need a contract. Good man. We need a contract, ladies and gentlemen. We need a contract. We need something that we can count on an ongoing basis about this calls that. And ladies and gentlemen, if you go and you look at this book, Effective Java by Block, it is shown in there, several examples, but you can go to the Java library, you will find exactly that sort of thing in the Java library, where when they build a class for subclassing, they need to provide more information in the specification than if it's just instances of it being used by your code. If your code could subclass this, not only do they have to provide preconditions, postconditions, and variant history properties, all that good stuff that's provided if you're using an instance of it, not only that stuff if you're serving as a client in terms of using instances, but for subclassing it, if you want to subclass it, they have to provide information about what calls what, who calls what. And the point is, by promising that, you know, as an implementer of a subclass, what you can count on. That I can count on that add all does call add, so if I override add, it's going to be called by add all. Yes?
So what happens if we have a superclass and it's out in the wild and people have written, subclasses for a while, and then we have a contract, and then later we discover, say, a vulnerability or something, and we need to change that superclass, we need to change the contract. What happens? Like, what's the best approach to dealing with it?
So it's a good question. So one way is to do what Java did with their date infrastructure, which they have this class called date, which is pretty broken, to be honest. It's a pretty broken class. It has lots of problems associated with it, which people have looked at, analyzed, among other things. I think it's not thread safe, etc. What they did is they created another class that offered a much better implementation. People could still use date, but now there's this other class that is a much better implementation, and the old one still circulates. That's one option. The other option is to say, sorry, yeah, I gotta evolve this interface. And that goes on a lot. Ladies and gentlemen, I'm sorry to tell you, but interfaces sometimes evolve. The Windows API was famous for this, right? You go through releases of Windows, major releases, and occasionally it would break something. And they would try to partner with their developers. They try to get a developer community, know who's using their code, talk with them, let them know this is going to be coming, give them time, give them the ability to detect what version of the Windows API they're working with, and evolve their code. And you know, in general, if you're going to evolve an interface, it's a big deal, because suddenly code that used to work breaks. And you may have code from all sorts of people over the world, all over the world, you don't know. You don't know that they're counting on your code, and you change the interface and it breaks. Changing interfaces is very, very delicate, serious matter. And you know, yes, it does happen. When I upgrade my Linux box, I periodically upgrade my Linux kernel. I'll probably do it later today. And I've heard, I don't know, but I've been told that it's going to break VirtualBox. Which happens to be what I'm running this in right now. So I chose to do it before, I chose to do it after class, not before. So the point is, it's breaking an interface. What happens is that it literally changes the signature of a function or something, so it can't compile VirtualBox for the new kernel, and it breaks. That's changing an interface. It's really inconvenient for me. In general, if you have interfaces, they are things that are contracts that are longer term in their implication, and you need to be very clear in thinking through what you promise up front, because you know, evolving it has great gravity associated with it, and you need to be really careful about promising what you promise. But here's another thing you can do, Janelle, and we'll talk about this more in 470. You can write an interface, but basically warn people, do not count on any of these types of things remaining the same. So you can explicitly warn them, you know, these are things you should not be counting on. So right now, maybe this appears to be an immutable class, but you should not count on that, because we want to allow for evolution in that regard if we think, say, it would offer performance advantages. So we basically warn the people who use this class or subclass it, do not count on this feature.
So write a contract about using a contract?
That's right. Well, it's not so much write a contract. It's just as part of your contract you say explicitly, do not conclude these things, do not count on these features. The contract's all about telling you what you can count on and what you can't, by extension, can't count on. Sometimes that's left up to the person to reason about. They say, oh, look, in this class, there's no methods to change things, to set things, or to modify things. This must be an immutable class. So people come to those conclusions. And you can explicitly say, do not count on this, and warn them, and head off that sort of assumptions in their code, which gives you the flexibility to evolve things. Okay. So very little time left. We're going to explore this more in 470. But we noted here the inability to create a mock or fake for a superclass and unit testing. If A uses class B via inheritance, we don't have the option of testing A against a proxy for the superclass. And as a result, we kind of have to test both together. And that means testing A, the subclass, with methods associated with superclass B and making sure that they work properly. And whenever B is changed, the superclass needing to rerun those tests for A. Because the superclass changing, you know, add all, how add all is implemented here, that could change whether your code breaks or works. And so you need to rerun the tests, you know, every time the superclass evolves, not just when your code evolves. Okay, so I have a set of suggestions here for planning for quality subclassing. You know, perform very thorough inspections of subclassed code. Specify distinct subclassing interfaces. If you're going to design a class for subclassing, be clear about what calls what, etc. And either design clearly for subclassing or prevent it. You can declare a class that is not subclassable by declaring it a final class. You say this class is final. It cannot be subclassed. And that's the safe thing to do. If you haven't thought through what you need to do to subclass it, to have it be amenable to safe subclassing. And as I note here, there's a set of sort of testing prescriptions for subclassing that go beyond testing for subtyping in terms of promises to in terms of testing. So when the subclass changes, test the superclass functionality, and when the superclass changes, test all the functionality of that class. Those are two of the most important features here. Okay, and confirm proper initialization of the superclasses, as that's often an oversight. Okay, that's all we have time for this class session. I will be back here for your presentations, and I much look forward to them. Thank you very much.